So, welcome back to the final lecture on probability theory with actuarial applications. This is week 12 lecture 5 and we will consider today part 3 of our discussion of the mock test, which is questions 21 to 21 to 30, right. So, let us move on. So, what we have done in last two classes, let us introduce that. So, this is the final lecture. We have only 10 questions left in our mock exam, which are questions 21 to 30, and in last two lectures we always adopted a 3-minute mindset. First, what is a topic, second, what is a tool that I will use, and third, with this tool is there any trap. Okay. So, always keep this mindset in your mind and try to solve the problems. That will effectively speed up the problem solving speed. Okay. So, let us move on to question number 21. Question number 21 actually suggests that the portfolio has 3 types of policies: type A1, A2, A3, type 1, 2, 3. Then the probability of claim in each of the type of policies is given to you, and you are interested in finding what is the overall claim probability, which is probability of C, for the randomly chosen policies. So, where is this problem coming from? So, basically I have to submerge over all 3. We can actually use a Venn diagram. So, I have A1, A2, A3, A1, A2, A3, and I want to find probability of C. This circle is C. So, how will I do? The law of total probability is the answer, which is essentially probability of C equal to probability of C intersection A1, A2 and A3. Though it is not specifically mentioned, but we are assuming that two types do not have any overlaps. Okay. So, that is where this formula is applicable. Can I compute these probabilities? The answer is yes. How will I compute them? Basically, that is where the law of total probability comes. It says it is C given A1 into probability of A1 plus C given probability of C given A2 into probability of A2 plus probability of C given A3 into probability of A3, correct. So, then it is just a matter of substituting these values and getting the correct answers. So, let us substitute. C given A1 is 0.05 into 0.5 probability of A1, okay, plus C given A2 is 0.1 into 0.3, and third one is 0.2 into 0.2. Okay. So, the numbers are quite interesting. This is 5 by 100, this is 5 by 10. So, it is 25 by 1000. This one is 1 by 10 and this is 3 by 10. So, this is 3 by 100. The next one is 2 by 10 into 2 by 10. So, 4 by 100. Okay. So, I will add one more zeros here, and then 40 plus 30 70, 70 plus 25 95. So, it is 95 by 1000. Is there any answer corresponding to this? Right. So, B is the correct answer. Okay. So, we can also write this in a printed form like this. It is very simple. Once you guess this is the law of total probability problem, essentially it is weighted average, and you just have to enlist all the terms and write appropriate numbers. Wonderful. So, we have solved question 21. Let us move on to question 22. Okay. This is related to CDF. You have been given a CDF of a random variable and you are asked to compute one probability. Very simple. So, now probability of x greater than 2 Can I relate this with some CDF? The answer is yes. This is actually equal to 1 minus probability of capital X less than or equal to 2. What is this? This is 1 minus F2. Can I compute F2? Of course yes. What is F2? Fx is this. So, I will simply substitute x with 2. First I need to basically check whether this is in this range or not. If it is not in the range, then you have a ready-made probability that is given to you. Okay. So, F2 I know this is in this range. So, I will substitute it is 2 square minus 1 upon 8, that will give me 4 minus 1 upon 8, that is 3 by 8, and now I will use this number F2, substitute it here, 1 minus 3 by 8. So, this gives me 5 by 8. Any answer related to 5 by 8? Yes. So, this C will be the correct answer in this case. Again, very simple problem, very straightforward, within 1 minute you should be able to solve it, and this is how you can implement our strategy. Perfect. Let us move on to question number 23. Okay, let us read that question. Claim arrivals follow Poisson process with mean rate 6 claims per hour. Okay. Find the probability that exactly 2 claims arrive in 20-minute period. Okay. So, here is the twist, 6 claims per hour and this is hour, so 60 minutes, and you are asked to find 20 minutes. Okay. So, an hour will be divided into 3 parts, of which one part is being given to you. Okay. So, now first, what is the distribution here? It is a Poisson process, Poisson with rate lambda t, okay, and this t denotes the time in hours. Now, this time in hours is basically, if t is equal to 1, this is Poisson lambda, but if t is equal to 20 minutes, what will this be? So, that is where our problem, where we are asked to find the probability in 20 minutes, this will be lambda divided by 3. So, I have a random variable which is Poisson, x follows Poisson with lambda divided by 3. Okay. What is lambda here? 6. Okay. So, 6 divided by 3 will be equal to x follows Poisson 2. 6 by 3 is 2. So, x follows Poisson 2. Then what is asked? The probability that this random variable x is equal to 2. Do I know the answer? Yes, I know, it is e raised to minus 2 into 2 raised to 2 upon 2 factorial, right. So, remember that formula, e raised to minus lambda, lambda raised to x upon x factorial. Okay. Here lambda is actually 2. Okay. So, if I know this formula, then this 2 factorial will cancel off this 2 and this becomes 2 e raised to minus 2. Any answer similar to that? Yes, A. So, I have A as my final answer, correct. So, we can do this in a way, this is the proper way. So, we must scale lambda, and I have already done that, and therefore, y follows Poisson lambda equal to 2, and then it is just a mere algebra that will give you the correct answer. Let us move on to next question, problem 24, where you have been given a joint density of 2 continuous random variables f x y equal to 2x plus y, where 0 less than x less than y less than 1. Okay. So, here is a catch. Okay. X and y are dependent random variables. What you are asked to find? So, this is a trap, you must be aware of this. Probability of x less than 0.5. Now, whenever such problem comes and this dependence is there, you should, as a rule of thumb, you should always plot the domain. So, this is x, this is y, and this is the line, say y is equal to x, sorry, this is the line, say y is equal to x. This is my x, this is my y. So, what domain we are talking about when we talk about x less than y? So, if you look at this, range of y is sealed at 1. So, I will assume this level is 1. Okay. So, this is one level. So, y is equal to 1 here, and you can also assume x is equal to 1. So, that becomes a square. So, this is a square. In this square, x is going to be always less than y. In which zone that is happening? So, that is happening typically in this zone. See, x is less than y all the time. Now, why I am doing this? Because probability of x less than 0.5 is asked. So, essentially I am asked to find some marginal probability. So, how will I find that? So, basically probability of x less than 0.5, if I write this as a joint distribution, this is also equivalent to saying basically y less than 1 less than 0, right. So, because this has 0 to 1 zone. Okay. Now, the interesting part comes. So, 0 less than y less than 1. That means, if I want to write this, I have to write this as a integral, as a double integral. So, this will first integral will start from 0 to 0.5, which is related to x, okay. And the second integral will be tricky, because you see the lower bound of y always starts from x. So, I have to write this from x to 1, and then this fxy joint distribution will be active, 2x plus y dy dx. And in order to evaluate this probability, you essentially have to integrate out this dy term, right. So, I will pull this over here, which is this. So, the factor of 2 is a constant factor. So, I do not worry about it. So, integral 0 to 0.5 as it is, and then I have integral from x to 1 and x plus y dy dx. So, let us focus only on the inner integral. So, I will pull this inner integral out, and what will this be? So, first term x with respect to y is a constant. So, this essentially will be this inner integral will essentially turn out to be equal to x as it is and y, where y is varying from x to 1, plus the second term. What is the second term? Which is y. So, this will become y square by 2, and it is varying from x to 1, okay. And this is my inner integral. I will first solve that inner integral, so that I will get rid of y and then substitute everything in there, okay. So, what is the solution? X will remain as it is. If you substitute 1 here, this remains 1, and minus x, 1 minus x, okay, plus y square will become 1 square by 2 minus x square by 2, okay. So, this gives me x minus x square plus 1 by 2 minus x square by 2, okay. So, x square minus x square, okay, this gives me x minus 2x square, this is 2x square by 2 minus 3x square by 2 plus 1 by 2, okay. Okay, so this is correct. So x minus 3x square by 2 minus 1 by 2, and therefore this inner integral is actually evaluated. So I will use the outer integral, this 2 will remain as it is, 0 to 0.5, and now inside instead of that square bracket I will put this particular expression, which is x minus 3x square by 2 plus half, and then comes dx. Then how will you solve? It is very simple. Then it is a straightforward algebra that you have to execute. So 2 will remain as it is, and then this x will become x square by 2 minus 3x cube by 2 into 3 again, okay, plus half x. So it is x by 2 evaluated from 0 to 0.5. Okay. Then you can easily do this, which is 0.5 square is 0.25 by 2 minus 3 gets cancelled, x cube will be 0.125 by 2 plus 0.5 by 2, that is 1 by 4. So it is 0.25. Okay. But let us put it 0.5 by 2 for ease of calculation, 0.5 by 2. Okay. So this 2 gets chucked off with this, okay, and then what you are left with is 0.25 minus 0.125 plus 0.5. So together this is 0.75 minus 0.125, which approximately is equal to 0.625. It is not approximate, it is exact. So the answer should be D. See, this is computationally tedious, and the consideration of x dependent on y was very crucial here. Okay. So this can take more, this if because we are doing these computations, it may take more than 3 minutes, but one question is okay. Okay. So what was the first step in this? First you have to visualize the zone. Once you understand the zone where the PDF is active, then you can easily solve the problem. Okay. And to solve the problem, you have to essentially know integration in a fast forward manner. A thorough knowledge of integration is required. Other than that, nothing else is there. Okay. Okay. Let us move on to the next problem, which is question 25, and this is x1, x2 are IID continuous random variables within the zone 0 1, interval 0 1, where they have CDF fxx equal to x cube for 0 less than x less than 1, and y2 is essentially maximum of x1 x2, and you are asked to find the density of fy2. Okay. So because it is max, so probability of y2 greater than y is what? Basically max is greater than, sorry, I will talk about this. Probability of y2 less than or equal to y is what? Okay. Maximum of x1 comma x2 less than or equal to y. That means the individual terms also must be less than or equal to y. This we have done when we did order statistics, and this essentially means, because they are IID, this essentially means its probability of x1 less than or equal to y into probability of x2 less than or equal to y. But what are they? They are basically fx of y and fx of y squared, right. So this is the CDF of our order statistic, which is y2. So this is going to be fy2 of y. Okay. So with this knowledge, this is actually a formula well known to us. You should recollect this formula, but for sake of convenience I have derived this formula. So now what is a PDF of this? This CDF of fxx is x cube, right. So, it is x cube, that means fxx is equal to x cube for 0 less than x less than 1, 1 for x greater than or equal to 1 and 0 for x less than 0, less than or equal to 0, right. So, this is the standpoint. So, what will be f y2 of y? F y2 of y will be x cube squared, correct, x cube squared, but x is not there. So, it is y, so it will be y cube squared, which essentially means this is going to be y raised to 6. Okay. Have I done? No, I have been asked to find the density. So, what I will do? I will differentiate this particular number d dy of this, which is d dy of this, which is d dy of this. Okay. d dy of y raised to 6 is 6y raised to 5, correct. 6y raised to 5 will be my answer. What will be the range? It will be 0 less than y less than 1. Very good. If there is any answer corresponding to this, yes, B is the answer corresponding to this. So, we have solved this problem also with correct answer B. Method of solution is given here. Very simple. You just have to relate this. I took 1 minute to actually derive this, that is why slightly more time is taken, but if you remember this, you are straight away. Even if you do not remember, we can still solve this in 3 minutes. Let us move on to the next question, which is related to law of total variance. Wow. So, given capital lambda is equal to small lambda, we have y given lambda is Poisson lambda. So, whenever Poisson comes, you should be on alert that your computation is saved. With the parameter satisfying expected value of lambda equal to 2, variance of lambda is equal to 1, and you are asked to find variance of y. So, variance of y, conditional distribution, law of total variance, that is the tool, no other tool exists. So, let us list what is law of total variance. Variance of y is equal to expected value of variance of y given lambda plus variance of expected value of y given lambda, right. So, this is the basic thumb rule. You list this. Can you relate to this? Variance of y given lambda and then expected value of y given lambda. Let us go in that order. So, expected value of y given lambda equal to small lambda. Do I know that? It is told to me that this is Poisson lambda. So, this is going to be lambda. Now, you bring in that version where we have this random variable itself is not without realization, that is this will be capital lambda, right. Similarly, we will talk about what is a variance of y given capital lambda is equal to small lambda. Again it is a Poisson, which is mean and variance are same. So, this is again equal to lambda. So, that simply means if I talk about variance of capital Y given lambda as a random variable, it will again become capital lambda. Wonderful. That simply means if I use this particular thing and plug those values in here, what does this mean? Variance of y given lambda is lambda. So, the first term is essentially expected value of lambda, and variance of expected value of y given lambda is again lambda. So, the second term is variance of lambda, and do I know these two terms? They are readily given to me. So, it is basically 2 plus 1 equal to 3. How simple is this? That is this B. B is the final answer. Okay, this is the solution of question 26, and you can easily see how we have beautifully used all the data that is given and plugged the values into law of total variance, and seemingly difficult task of computing variance of y became very easy. Okay, that is the power of tools that we developed. Let us move on to question number 27, which is okay. So, x is normal distribution with mean 10 and variance 4, y is normal distribution with mean 20 and variance 5, and they are given to be independent. So, z is equal to x plus y, and you want to approximate and find the probability of z greater than 33. However, this question there is actually no approximation, because we can actually evaluate this value, because I already have a normal distribution. I also know the normal if given a normal distribution, the sum is also a normal distribution. So, there is no confusion in this. You do not really require MGF of sum is normal. You simply know the reproducible property of normal distributions, and therefore, x plus y will follow normal distribution. I just need to figure out what is a mean, what is a variance. So, that is the main task. So, essentially the resultant, if you call that as some w equal to x plus y, then mu of w will be equal to mu of x plus mu of y, which is 10 plus 20, which is equal to 30. No brainers here. Sigma w squared will be equal to, because they are independent, sigma x square plus sigma y squared. One is 4, one is 5. So, together it is going to be 9, right. So, I have normal with mean 39, which is my z. Okay, here it is z. So, I will replace this with z. Okay. So, I have replaced it with z. So, now I want to find probability of z greater than 33. No continuity correction needed, nothing needed, z greater than 33, it is actually a normal distribution. So, what I have is probability of z minus the mean upon r. So, here is the trap, sigma square is 9, sigma is 3 divided by 3 greater than 33 minus 30 divided by 3. Okay. So, this simply reduces to the standard normal random variable z standard greater than 3 by 3, which is 1.0, which essentially means this is 1 minus capital phi of 1.0. From normal table you can easily get the value of phi of 1.0, which is going to be 0.8413. Therefore, the final answer will be 0.1587, which essentially means 15.9%. This is A is the final answer of this. Here it was very simple. You do not really require MGF ideology here, but with MGF also you can show that sum of these two random variables is a normal random variable. Okay. So, this here is a solution with MGF property into mind. This is the solution. Okay. You can go through it. Okay. So, let us move on to question number 28, which is related to CLT. S is Poisson 100. Okay. 100 is a large number. Therefore, you can view this as sum of 100 Poisson 1 random variables. Can you use normal approximation with continuity correction to compute probability of S less than or equal to 90? The answer is yes. Okay. So, what is a tool here? CLT, and the trap is continuity correction. So, probability of S less than or equal to 90, how will I map this to approximate normal? This is probability of Y normal less than 90.5. So, you already know I will splash over this 0.5 here, 0.5 there if there is a unit step. Okay. Poisson has a unit interval in between 0 to 1. Okay. So, that way I have actually taken into account continuity correction. Because it is Poisson, you do not really have to worry. What is mu s here? Poisson 100, it is going to be lambda, and variance also is going to be lambda, right. So, no specific computation, only thing that is required is y normal less than 90.5. So, you can also, because it is a continuous random variable, you can also say less than or equal to, because that will help me in quantifying the terms. So, you start with probability of y normal less than or equal to 90.5, and this is essentially equal to probability of y norm minus what is the mean 100, what is the variance 100, but when I am doing this, this will become square root. So, it is 10 less than or equal to 90.5 minus 100 upon 10. So, that effectively gives me probability of standard normal z less than or equal to minus 9.5 upon 10, which effectively means probability of z less than or equal to 0.95 with a negative sign. Okay. So, this is slightly tricky, but this you can always, because of the symmetry property of normal distribution, can relate to probability of z greater than or equal to 0.95, and therefore, you can use the same standard normal table, and this will be 1 minus capital phi of 0.95. What is the value of 0.95? It is 0.8289, 1 minus of that. So, that will give me somewhere around 17%, 1711. Okay. So, this is the value. Okay. So, I got the answer, correct answer to be equal to B. So, this is how you will solve the problem. We have used the topic is central limit theorem, trap was continuity correction, and this is Poisson approximation to normal approximation to Poisson. Okay. Let us move on to the next question, which is question 29. You can go through the solution, which is in printed form, 4-step solution, and let us move on to the next question, which is related to layer policy. So, I have an exponential distribution with mean 100, policy has deductible small d equal to 50, limit is equal to 200, payout per claim is given by this expression, which is given here, and you want to essentially find the pure premium for this policy, that is expected value of y. How will you proceed? First of all, it should stagger into your mind that this is exponential distribution. So, we have some easy way outs for exponential distribution, and when this exponential distribution comes, this expected value of x and k, minimum of x and k, which is given there, is actually equal to expected value of x into 1 minus e raised to minus lambda k. Okay. So, if you know this trick, then the computation is just a cakewalk. So, what is it? That basically expected value of y, if I want to compute, because expectation is linear operator, this is effectively expected value of x hat d, which is 200. So, hat 200 minus expected value of x hat 50. Okay, sorry, this is u and this is d. Okay, so this is given to you, perfect. Then because it is exponential distribution, you already know the first term, this is 200. So, I got 100, which is the expected value given here, into 1 minus e raised to minus lambda k. So, lambda is 1 by 100. So, 0.01 into 200, okay, minus, again the same logic applies. So, I will take this 100 common, 100 is common, and this is 1 minus e raised to, lambda will still remain the same 0.01 and multiplied with 50, okay, then the square bracket is complete, fine. Then I have to just reshuffle the things and get the final answer, very good. So, 100, now you look at this 1, this will mutually cancel each other off, this negative sign will become positive sign. So, e raised to, but this is 1 by 100 into 50, that gives me 5 by 10, that gives me 5 by 10. So, it is e raised to minus 0.5 minus, this is 1 by 100 into 200. So, this will give me e raised to 2, e raised to minus 2, right. So, therefore, this should be the answer. Is there any term corresponding to this? Yes, A is the term corresponding to this. So, answer A is the final answer. See, because I knew this shortcut, my job was very easy. Otherwise, I have to compute all this. If you are using survivor function, you have to go through the lengthy computations. So, this trick significantly saves my time. Okay. So, here is the printed solution for this. You can go through it at leisure. Okay. Now, let us move on to the last question, which is the last part of this particular section. Okay. So, here is a question, n follows Poisson with lambda equal to phi, this be the claim count, the number of claims basically, and for each claim the payout y satisfies expected value of y is equal to 50, expected value of y square is equal to 4000. Okay. The aggregate loss S is random sum of these yi's, where the summing variable is Poisson. Okay. Now, you are asked to find variance of S. So, I basically do not know the distribution of y, I just know the two moments of y, and the summing variable is Poisson. So, naturally a compound Poisson shortcut is the key to figure out what is variance of S, and in that case I know variance of S will effectively be lambda into expected value of y squared. Perfect. Then do I need to calculate anything? It is very simple, right? Expected value of y square is given to me, Poisson phi, so lambda is equal to phi. So, essentially this problem is nothing but 5 into expected value of y square, which is 4000. So, that gives me something like 20,000. Is there any answer? Yes, and therefore, answer B is the correct answer. See how simple is our world if we know proper tools and techniques. So, within just 2 lines I have solved this problem. Okay. So, this is the printed version. The analysis part tells you how to use the compound Poisson variance shortcut, and the solution is just a multiplication of 2 terms which are already given in the problem. Wonderful. So, what we have done so far is we have completed the course. We have this lecture is the third part of the mock exam review. We have all 12 weeks of our course are into this mock test. So, we have covered the entire syllabus. What our journey so far was, we started with simple axioms, the language of risk, and then we understood how this language of risk is probability, the axioms are the grammar of this language, and then we delved with some probability concepts such as counting and all those things that we did in weeks 1 and 2. Then in week 3 we built a toolkit with special distributions. Week 4 we learnt how to model the systems of risk, and week 5 we continued the same through joint distributions. So, we had a basic toolkit ready by the end of week 5. After that, we learned some power tools, namely law of total expectation, law of total variance in week 6, and the magic tool, which is the moment generating function and the cumulant generating function, in weeks 7. Okay. So, week 6, 7 we developed a power tool kit. Then even if we have incomplete information, during week 8 and 9 we learnt how to estimate probabilities, how to give bounds on probabilities, and how to understand the overall long term behavior of random variables. That was our key motivation in weeks 8 and 9. And finally, in weeks 10 and 11 we essentially dealt with random sum, and that random sum we gave the actuarial perspective, and we saw how to design a master algorithm for real world insurance policies. That was our contribution, and we have completed this course. So, what are the next steps from here? First of all, let me wholeheartedly congratulate you for completing this course. You have now a complete theoretical understanding required for exam P. Your knowledge is complete, but you may not be fluent. How will you bring in fluency? It is not about knowing how to solve a problem, but to practice it and do it quickly and accurately. So, that is how you will bring fluency in your understanding. Okay. So, what is a strategy that we equipped you with is a 3-step strategy. Every time you see a problem, you identify a topic. Second step is you identify a tool, and third thing is whatever tool you have chosen, is there any trap associated with that tool. So, topic, tool, trap, this is triple T mindset will help you to solve all the problems, and this strategy will actually speed up your problem. We have used some of the study materials available in Broverman and Finan, which are very popular in the actuarial context. So, you can also use that study material, and thank you for your dedication and hard work by listening to these lectures, and good luck for your exams and in your future career. Thank you very much for listening to this particular lecture, in general for taking this course as a whole. Thank you very much.